Hi everybody, this is part 2 for Module 5 for Math 026. This is our last video that you will see for this course. We are almost done. Woohoo! So for the second part, we are going to first look at graphing logarithmic functions, and then we are going to look at applications with exponential functions. So in order to graph a logarithmic function, you want to write the logarithmic function as an exponential function, and then graph it using the table of values. So here we have the log of x with base 2. So remember, if I rewrite it, it's going to be 2, and we're going to take that f of x and make it our y, to the y power is equal to x. So here you'll notice they helped us out a little bit. We don't need x values, or it would be easier if we have the y values, and that's what they gave us. So we're going to start off 2 to the negative second power is equal to x. That's going to be 1 over 2 to the second, because we're going to get rid of that negative exponent, or 1/4. So we'll put our 1/4 there. 2 to the negative first power is equal to 1/2. As again, you flip it to make it positive. 2 to the 0 power is always going to be equal to 1. 2 to the first power is going to be equal to 2. And 2 to the second power is equal to 4. So we are going to graph this. So we have x is 1/4, and then y is negative 2. So again, this is going to be kind of like an estimation there. It's really where that first pen mark went. Negative 1, 1/2, or 1/2 negative 1. So it's right there. 1, 0 will be right there. 2, 1 will be right here. And then 4, 2 will be right there. So now we're going to draw that line, and it should not cross over that y-axis like mine did, but again, it's the inverse of the exponential function, 2 to the x power. So domain and range. Domain is your x values. If you notice on the x-axis, it's never going to cross over that 0. It's never actually going to hit 0. So my domain will be 0 to positive infinity. And my y values is going to keep going up, and it's going to keep going down. So your range here will be negative infinity to positive infinity. So the next one we are going to do is the log of x with base 3. So if I rewrite it in exponential form, it would be 3 to the y power equals x. And again, we're going to plug in the y values they gave us. So 3 to the negative second power will be 1 over 3 to the second, or 1/9. 3 to the negative first power is equal to 1/3. 3 to the 0 power is always equal to 1. 3 to the first power is equal to 3. And then 3 to the second power is always going to equal 9. So now we're going to go ahead and graph this. And it is going to be very hard to put that 1/9 negative 2, but we'll try it out right there. 1/3 negative 1, it'll be like right there. 1, 0 is right there. 3, 1 is right there. And then 9, 2 will be right there. So again, when I graph it, it's going to look like this. It's going to ride right along that y-axis, but never touch it. And here, again, your domain and your range will be the same. It's going to ride right up to that 0, but never pass it, and it will be to positive infinity. And then the range is going to be negative infinity to positive infinity. right, so now we're going to look at applications of exponential functions. And first, we're going to talk about compounding interest. And this is a very good real-world application. You know, we all talk about gaining interest. Compounding interest is great because you earn interest on not only your principal, but any other interest you've received in the past. So the formula that we use to figure out compounding interest is A is equal to P. Now, A is the amount in the account at the end of the time you're calculating. P is the principal. That is the initial amount you put into the account. So if I put $500 in, that would be P. Times 1 plus the rate, which is your percentage that you're earning in the account in a decimal form, divided by N, which is the number of times it is compounded per year. And that is all raised to the NT power, which N again is the number of times compounded per year. And T is the length of investment, and you always want to put that in years. The hardest part here is making sure you have the numbers in the right spot, and then you follow order of operations to calculate it. Okay, so here we have Jenny, and she puts in $1,000 into an account that is compounded quarterly at 3.1% interest. If the money is left for 6 years, approximate the amount after 6 years. So how much interest would she earn, or how much would she have in the account? So remember, our formula is A is equal to P times 1 plus your rate divided by the number of times compounded raised to the NT power. So here I'm going to have A is equal to my principal. Jenny is putting in $1,000 times 1 plus my interest rate. It's compounded quarterly at 3.1%. So if I turn that into a decimal, move it to the left 2 places, so 0.031. It is compounded quarterly, so that means quarterly per year is 4 times a year. Think of 4 quarters in a dollar. And then it will be 4 times the length of time in years is 6 years. So the first thing I always do when I'm doing this is I calculate it in steps. I don't put it all into the calculator at once. And I am going to start off by figuring out what my exponent is. So 4 times 6 I know is 24. Now I need to do parentheses first. So I am going to do 0.031 divided by 4, division first, plus 1. And that is going to give me A is equal to 1,000 times 1.00775. And you never want to round this problem until you reach the very end. The more you round, the more your answer will be skewed. So even if you get a long, crazy decimal on your calculator, leave it until the very end. So now I'm going to take that 1.00775 and raise it to the 24th power. And that is going to leave me with A is equal to 1,000 times 1.20355 8942. 8942. And I left everything that was on my calculator. Now I'm going to multiply that by 1,000. And when I do that, it's going to leave me with $1,203. And it's going to be 0.558942. But we're talking money. So we are going to round it to $1,203, and that's an 8, so this becomes a 6.56 cents. So I invested, or Jenny invested $1,000. At the end of 6 years, at a 3.1% interest, she has $1,203.56. So she earned $203.56 in interest, which you're probably like, that's not very good. You're right, it's not, but most interest rates on savings accounts are less than 1%. So to have a 3.1% interest rate, that's a really good interest rate, and she's actually, she did pretty well for those 6 years. All right, so now they're asking which will have a higher return if you invest $20,000 for 3 years in an account compounded monthly at 2% interest, or in an account for 3 years and it is compounded daily at 1.5% interest. So let's start off for the monthly. We're going to use actually 2 different formulas here, but for monthly, we're going to do, again, our A equals P times 1 plus the rate divided by the number of times compounded times N times T, which is the time in years. So we'll have A is equal to $20,000 times 1 plus my rate is 2%, so 0.02 divided by compounded monthly means 12 times a year, raised to the 12 times, it's going to be in there for 3 years. All right, so that's the first one we're going to calculate. The other one, the formula stays the same, but the information changes. So we're going to have P times 1 plus the rate divided by the number of times compounded raised to the NT power. So again, we are investing $20,000. And the rate is 1.5 here, so that is going to be 0.015. Now for N, it is compounded daily. So with a year, there's 365 days, so it's per year, so 365. And then times, for our exponent, it would be 365 times 3. So let's go ahead and calculate the first one. And we are going to do our 2% interest rate, and it is going to be my 12 times 3 gives me my 36 for my exponent. So I'm going to do 200 divided by 12 plus 1. And that is going to give me A equals 20,000 times 1.0016666. I know it's a lot of sixes, I'm sorry. 7 raised to that 36 power. So now I'm going to raise it to the 36 power because you do exponents before multiplication. And so I am left with A is equal to 20,000 times 1.061783,515. And then when I multiply that times 20,000, I end up with, and I'm going to round it to the nearest cent, so it'll be $21,235.67 because it's 0.6703. Okay, so we ended up with like $1,235.67. So not bad. Let's look at part B. We're going to invest $20,000. For my exponent, we have 365 times 3. So that gives me an exponent of 1,095. It's crazy. Okay, so 0.015 divided by 365 plus 1 is going to equal 20,000 times 1.000041096, and we're going to raise that value to the 1,095th power. Again, I'm using my calculator because obviously we're not doing this by hand. So So now I have 20,000 times 1.0460268993. And when we multiply that times 20,000, we end up with, and I'm going to round it to the nearest dollar, $20,920.54 because it's 0.53785, but I rounded it. So at first I was like, oh, well, compounded daily, that's pretty good. But the interest rate was lower by 0.5%. So notice, even though it was compounded less, because the interest rate was higher, we actually ended up with more money by compounding monthly at 2% than compounding daily at 1.5%. And this is a good thing to test out when you're looking at different savings options and accounts with interest. You want to see which one's going to give you the most money for your investment. All right, now we're going to look at exponential growth. So we have a population of fruit flies that is initially 100, so there's 100 fruit flies, and it grows at a rate of 2% per hour. They want us to approximate the population after 6 hours, 5 days, and 75 minutes. The formula we are going to use is we're going to take our initial amount. It's called A of 0, but that's the initial amount. So in our case, we know that it is 100 fruit flies times 1 plus the rate of growth. So in our case, and you want it as a decimal, it's 2%, so 0.02. And then you're going to do your time. T is the length of growth. Now ours is per hour. So notice down here we have 3 problems to do. We have 6 hours, 5 days, and 75 minutes. But our rate of growth is per hour. So when we're doing our problems, this first one's not an issue. I'm going to put my 6 there and calculate. But for 5 days, I want that to not be in days, but I want it to be in the length of growth time. So it's going to have to be converted to hours. So if I take 5 days, times it by 24 hours in a day, we're going to use 120 hours here. And then 75 minutes, 75 divided by 60 to get hours is 1.25 hours. So again, you want to have your time or your growth in the same units as they give it to you. So that was like what would be a little bit different with these. And so for the first one, I'm going to do 1.02 because 1 plus 200ths. Raised to the 6th power, which is going to give me 100 times 1.1262419. And I'm going to times it by 100, so it's going to give me, now we're talking about the number of fruit flies, so you can't have half of a fruit fly, so we're going to round it to the nearest whole number. I end up with 112.6 if I round it, but I want whole numbers, so I'm going to say 113 fruit flies there. It's approximately. All right, let's try 5 days. So we would do 100 times 1 plus my growth of 2% raised to the 120th power. So 1.02 raised to the 120th power is going to give me 100 times 10.765. 16303. And if I multiply by 100, I'll end up with 1076.516303. But again, I'm talking fruit flies. I can't have half of a fruit fly. So 1077 fruit flies. And then after 75 minutes, or 1.25 hours, we would do 100 times 1.02, which is the 1 plus the rate, raised to the 1.25 power, so 1.02 raised to the 1.25 power. It gives me 100 times 1.02506219. And I multiply that by 100, it gives me 102.506219, which we would round to 103 fruit flies. All right, so now we're going to look at exponential growth. Or we looked at exponential growth. Now we're going to look at decay and half-life. So for our formula for decay, the formula is very similar to the one where it's exponential growth, except here, instead of adding the growth rate, you subtract the growth rate. That's the only thing that's different. You start with the initial amount, times it by 1 minus the growth rate, and raise it to t, the length of decay. So for A, we have a car is initially purchased for $25,000 and it depreciates by 15% each year. So they want us to find the value of the car after 10 years. So we know that we started off, we paid $25,000 for this car. And it depreciates by 15%, so 0.15. And we want to find the value after 10 years. And it says each year, so 10 years is good. All right, so 1 minus 0.15, or 15 hundredths, is 85 hundredths. So we have 25,000 times 85 hundredths. And in this case, we'll raise it to the 10th power. So we're going to raise that to the 10th power. It's going to give me 25,000 times 0.19687444043. And when I multiply that times 25,000, we end up with the car value after 10 years is $4,921, and I'm rounding to the nearest cent, 86 cents. Okay. Now, 30 months is not by years, and we want years. So I'm going to take the 30 and divide it by 12 so that I have the same unit as the depreciation is given to us. So 30 months is 2.5 years. So we'll take our 25,000 and times it by 1 minus, again, my 15 hundredths raised to the 2.5 power. So 25,000 times 85 hundredths raised to the 2.5 power. So 85 hundredths raised to the 2.5 power is going to be 25,000 times 0.66611287. And if I times that by 25,000, I'm going to end up with $16,652, and I'm going to round to the nearest cent, 80 cents. So that would be the value remaining after 2.5 years. All right, we're going to look at our final two problems here. And this one, we're going to deal with a radioactive element, and it has a half-life of 50 years. And if there is initially 1,500 grams of the element, approximate how much is left after 150 years, or this is also 3 half-lives, and then 144 months, which if, again, we divide by 12 to find the amount per year, and then divide it by our 50 years for half-lives, it's 0.24 half-lives. Now, half-life means that after 50 years, half of it is left. So our decay is 50%. So when we do this problem, we're going to take our 1,500 grams that we initially had, do 1 minus our 0.5 or our 50%, and then our time is going to be the number of half-lives, because that's what we're talking about. So we're going to have a 3 for the first one. And then for the second one, we're going to do, again, our 1,500 times 1 minus our half-lives, and then we're going to raise it to the 2400th power. So 1,500, or let's do 5/10 raised to the third power, because 1 minus 5/10 is 5/10. And then times 1,500. Okay, so we have 1,500 times 1.25. And then when we multiply that together, we get 187.5 grams of the element left after 150 years. Now, for the next one, we're going to take our 0.5, and because 1 minus 0.5 is 0.5. So we'll raise that to the 2400th power. And I end up with 1,500 times 0.84674533124. And then if I times that by 1,500, I end up with 1,270, and I'm going to round it to 2 decimal places, 0.12 grams of the element left. And that is it for all of the notes for Math 026 Module 5 and the Math 026 course. Yay!